In this video, we're going to look at the variational interpretation of expectation maximization. And we'll see that that interpretation generalizes other popular clustering methods like k-means. So we'll start, well, this is the outline. So we'll start by bounding the log marginal likelihood, which is the likelihood that we're going to be interested in really maximizing. And then we'll talk about different families of variational distributions that allow this bound to hold. In particular, we'll look at fully factorized distributions, which will lead to the EM algorithm as we learned it in the last video. But then we'll also look at point distributions, so distributions that have zero entropy and just have probability 1 at some point. And that will lead to a variant of expectation maximization called hard EM, of which k-means, or the famous k-means algorithm, is an instance. So let's get started. The marginal likelihood is what we're going to use as our ideal objective function that we want to maximize when we want to fit parameters to a mixture model. So I'm going to try to keep all the notation here very general, so it's actually going to describe many types of distributions that have latent variables. And I'll, as much as possible, connect it back to the Gaussian mixture model example. So the marginal likelihood is the likelihood of x given the parameter is theta, and we're just going to use theta as a general way to describe whatever parameters you have in your model. And this likelihood is going to, right, it doesn't, on the screen it doesn't involve any other variables, but we know that there exist some latent variables, z. So what this likelihood actually does is it sums out all the probabilities of z's. And here we've written it has an integral, but in many cases we'll be interested in discrete probability distributions, so we can write it as a summation. And the running example and the main motivation for discussing this idea is the Gaussian mixture model, where our data comes in the form of a bunch of data points. We have some our parameters come in the form of a bunch of Gaussian means and Gaussian covariances and some mixture probabilities, or a prior mixture probability. And our latent variables are the cluster memberships. The z's are the cluster memberships for each point. So for each point, it's going to have a multinomial variable that tells you which cluster it belongs to. And the marginal likelihood is then going to sum over all of the joint likelihoods of the x's and the z's, which will take this form. Right? So given a parameter theta, the probability of the joint state of x and z is going to be the probability of z times the probability of x given z. So going back to the general notation, we're usually going to be interested in the log marginal likelihood, which has this nasty summation inside the log, right? So it's a log of a sum, which isn't as easy to handle as if it were a log of a product or something. And our learning objective is exactly this, right? So we're going to try to maximize over all the possible thetas this objective function, the log of the sum over all latent variable states z of the joint probability of x and z, given theta. So this is hard. It's a non-convex objective function that we're trying to maximize, and the way that we do it in expectation maximization is we maximize some form of expectation. So let's get to what that is. But in order to get there, we should think about a general concept in the analysis of convex functions, which is Jensen's inequality. Actually, I believe the proper pronunciation is Jensen's inequality, but I will never consistently do that, so I'm just going to go ahead and be American and call it Jensen's inequality. So it says that if you have any convex function curly phi, if you take that function of an expectation, that's always less than the expectation of that function. Or more relevantly to our discussion, if you have a concave function, not curly phi, then the inverse is true. Right? So the phi of an expectation is going to be greater than the expectation of phi, where the random variable goes inside is the input to the function. And right, the reason that this is the more relevant form is because we're dealing with a log likelihood, and the log function, the logarithm function, is a concave function, at least for non-negative inputs. So we can use this to derive a bound for our log likelihood. So let's go ahead and do that. So we'll keep that up in the corner. And remember, our objective function is this. This is the log marginal likelihood. And we're going to use something a little bit weird because, first off, in order to use Jensen's inequality, we need to write out an expectation of something. So what can we can't really write this as an expectation. You could do some manipulation to do that, but what the typical trick for doing this type of analysis is to do something weird, which is to multiply each of the probabilities inside the logarithm, inside the log sum, to multiply each of them by 1 in a weird way, in that we're multiplying it by some distribution q of z divided by that value q of z, or not the distribution, but the likelihood of z under some distribution. So q of z over q of z is always 1, and q of z sums to 1. So what we can do is we can rearrange some terms here. So now this is the same thing. I just moved what was in the fraction around. Now we can see that this is an expectation, right? This is an expectation using the distribution q for the z variables of the joint likelihood of x and z divided by q. Pretty weird, but that's the trick. So if that's the case, then we can apply Jensen's inequality using the q distribution. So we end up with, right, so this was the log of an expectation. Well, now we're going to turn it into an expectation of a log. Right, so now it's the expectation under that q distribution of the log of this likelihood ratio. And then the logs break apart nicely. The terms in the fraction inside the log break apart nicely into two separate terms, and you can write it out as in the following form. So far this whole thing is true for any distribution. We haven't said anything about what Q is. We just said that it's some distribution over the entire state space of all of the latent Z variables. But we ended up with this bound. So the bound is like this, right? So the original true marginal likelihood on the left, or log marginal likelihood on the left, is going to be bounded by the sum of these two summations, right? The difference of these two summations. And the first term is an expectation of the log joint likelihood, and the second term is actually an entropy, right? This is the entropy of the Q distribution. And all this strongly connects to concepts like the Kullback-Leibler divergence and mutual information and things like that. But we don't have to worry about that right now. We can just treat this objective function as it's written on the page. And the idea is that this is true for any Q distribution. So we can pick any Q distribution and this bound is still true. Right? We're still lower bounding the original objective function we cared about maximizing. So the strategy then is to replace the original objective function, which was to try to just maximize the non-convex log marginal likelihood, with trying to maximize this bound. Right? So now we're trying to find the parameters theta that maximize the likelihood, but at the same time we're trying to pick the parameters q that maximize this lower bound, where the Q distribution is treated as a parameter. And I believe, I'm not completely certain about the history of the naming of this whole methodology, But my understanding, which may be wrong, is that the reason that all this technique is called variational is because it ties to the calculus of variations, which is calculus on functionals. And in this case, we're considering the function q, right? Q is a distribution, which is a function, to be a parameter. So this whole objective function is a functional, I think. So now I don't know that the technicalities here and the history. So, but this is known as a variational method. Now, we can now think about what types of Q distributions would be interested in doing this with. And right, the way that it's written on the page, the types of Q distributions are, it could be anything, and it's actually a huge space of possible distributions because we're talking about the distributions over all the possible joint states of Z, right, capital Z. So that's, if you have n data points and the Z's represent cluster memberships, and there's I don't know, k possible clusters, then there's n times k possible variables, and on a rough estimate, I think you have k to the n possible valid joint states. So that's a huge amount of space a huge state space. But usually what we like to do is we make a simplifying assumption that the Q distributions factorize. So we say that there's like a big Q distribution that's over over the capital Z space, and that factorizes into the product of all these independent Q distributions for each Z variable. And we say that each little mini Q distribution sums to 1 appropriately. And that leads to the fully factorized variational family. And the whole idea here is we want to, while we say that we want to maximize this, this objective function with respect to theta and with respect to Q, if we limit the space of possible Qs, or capital Q in the way I wrote it, if we make capital Q a restricted subset of all possible joint distributions, we make our lives easier, and it becomes computationally feasible for us to solve this optimization. Right, so we say that it has to be fully factorized and that it sums to 1, and then we end up with something that breaks apart into these little pieces. Right, so now for each data point, we have its own log likelihood times its own scaled by its own Q distribution, right? So its expectation with respect to its own little Q distribution, and we have little Q entropies that that only depend on one data point at a time. And this, if you do the math out, which is part of your homework assignment, you'll find that you get the exact update equations for Gaussian mixture model EM if you look at this objective function, or if you optimize this objective function. So this is nice, but the other thing I mentioned is that any distribution is a valid lower bound, and therefore that also means that any family of distributions could be a valid, or would lead to a valid strategy for approximately optimizing the log marginal likelihood. So what we can do is we can say that capital Q, the space of all valid distributions we're going to consider, is going to be fully factorized like before, but we're also going to say that it's going to be point distributions. It's going to be distributions that are 0 everywhere except for one possible state, right? So the way that I've written this is that there's going to be some states Z hat of I that are the states that get one probability, a probability of 1.0, and every other state gets 0 probability. So, these are point distributions or delta distributions, or there's lots of other names for these, but they have 0 entropy, right? So their entropy is 0, and they either evaluate to 0 or 1, so you don't have to sum over all the states, you just have to consider the state that has non-zero probability. So when you look at the objective function, this simplifies a lot, right? The entropy disappears because it has 0 entropy, and then the summation over all zi's is only going to be true, or is only going to be non-zero. The terms in the summation will only be non-zero when zi equals z hat zi, right? So you end up with this very simple objective function. And in English, you can read this out, and what it says is that for every point, we're going to sum up the log joint likelihood of the point and zi and some hard assignment to the cluster assignment variable, the cluster membership variable. And this is nice in some ways because it's really easy to compute. Right? It's really easy just to pick the maximizing zi assignment, which becomes zi hat. And in the Gaussian case, that's basically just picking the closest mean to any point. But the downside is that this is a lot less robust. It's not as nice of a lower bound as the fully factorized form, fully factorized multinomial form that we use that leads to the EM algorithm. And what people like to do in practice is that since this is such a simple method, they will do this in such a way that further simplifies. So let's try plugging in some of the distributional components of the Gaussian mixture model into this hard expectation maximization variant. So if we look at the joint likelihood of z hat and x, we get something like this. Now here I've thrown away the prior distribution just to make things simpler, and we'll continue throwing away pieces. But let's just say that all the prior is uniform. So in this case, it would be proportional to this. And if you look at if you have this, then the update for z, the update to find the maximizing setting of the z variables is just pick the z that has the highest likelihood, the highest Gaussian likelihood. And then the update for the the means, is just take all the points that have been assigned to this mean, that have been assigned to this cluster, and take their average. Right? We don't have to weight them in any way because the weights are all either 1 or 0. And then the covariance is the same. You just take the covariance of the points that have been assigned to this cluster. And most of the time people don't actually go this far because they'll actually just remove the covariance altogether and just treat the covariance always to be just a spherical covariance. So this is the k-means algorithm. That's the super simple form of the hard EM approach. So step one is you pick the cluster memberships just by taking the means that are closest to all the data points. And then step two is you update the mean by taking the average of the points in each cluster. And you just repeat that until it converges. And that's the k-means algorithm. And there's lots of variants, right? You can imagine putting the covariance back in. You can imagine having a class prior, which would essentially act as some sort of distance threshold here. And those are all valid extensions to k-means. I believe there is some algorithm called k-means plus plus that's trademarked or something. I don't actually know what it does, but you can imagine it's just some variant on this approach. So just to give you a quick visualization of what this looks like, so this is a bunch of points that are generated. That's the input data, and as a human you can see there's some pretty clear clusters here. But the way k-means works is you initialize the means to some points, and I've drawn lines to connect all the points to the means, and then we can look at the different steps of the algorithm. So the first, or one of the steps, I guess the second step now, is now that we've assigned all the points to their closest means, is to look at each cluster one at a time. So we look at this cluster on the bottom right, and we say, well, we need to come up with a new mean for this cluster because this old mean doesn't seem accurate anymore to what we have. So the new mean moves over a little bit to the right. Then we do the same thing for each other cluster. So this cluster, all the points are on the top right, but the mean was someplace in the middle. So we update that mean to be in the average of all the points in this cluster, and so on. And you do that for all the means, for all the clusters. And after iteration one, we have these updated means. And you can see from looking at this image that at least this point right here, which I'm pointing at in green, looks like it's been assigned to the wrong cluster. And that's an artifact of where the means were in the first iteration. But now that they've been updated, now that they've been made consistent with the cluster memberships, the new cluster memberships don't seem consistent. So in fact, if we update the If we run another iteration of k-means, we will update the cluster memberships, attaching that one to the upper right cluster, and then update the means, and so on. And this whole thing repeats, iteration after iteration, and you can see sort of weird things happening as we reassign points to clusters and re-update the means of each cluster. And eventually you get to the point where you run the update and nothing changes. And that's when it converges, and that means that you've reached a local optimum, roughly. It's not exactly a local optimum because we're not really sure what we're optimizing is this very discrete objective function. So it's hard to call it a local optimum, but it's a fixed point where we can't make any improvement anymore. And it's definitely local in the sense that a better initialization might give you a better solution, or more accurately, a different initialization would give you a different solution. And it's kind of cool to watch, so I wanted to show it to you again in faster motion. So here's the animation. So this was the initialization, and you can see it sort of crawl its way toward the solution. And it's not super clear that this is necessarily the right answer. I think actually maybe we gave it 5 means or 5 clusters when really it probably would be better fit with 4 clusters. But it's hard to say. Okay, so to summarize, what we did here was we used Jensen's inequality, because I'm American, it's Jensen's inequality, to derive a lower bound on a log marginal likelihood. And that bound ends up using this variational distribution Q. Okay, and we get to choose a family of Q distributions to consider. Right? On paper, right, mathematically, we really should be doing it over the family of all possible distributions for the latent variables, but we don't want to do that because obviously that's super expensive. So we choose a simplified family of distributions that we can efficiently solve each of the steps of the maximization. So if we use a fully factorized multinomial distribution for Q, we get the EM algorithm. And if we use the fully factorized point distributions, we get the hard EM algorithm, which if we fix the covariance matrices to be spherical covariance and remove the prior, we get the k-means algorithm.